So I'm finally starting now the Year 2 mechanics videos, which I know a few people have been waiting for, but I've been trying to get the Year 2 pure things out of the way first. And we're starting with chapter 4.1 on moments. Now, I'm going to find this a bit of a difficult chapter to explain because in the classroom this is normally where I'm waving a lot of things around and sort of trying to tilt things to give you a picture. It's going to be a little bit difficult to do it on the screen here, but let's hope we manage that. But the idea of a moment is that it's a turning force. Now the big bit of advice I've got for you here is do chapter 4 exercise A carefully. Get a lot of experience of finding moments. And before you go much further into it, you maybe go on to 4B or something, but before you go very far, make sure you are very good at finding moments because they can be a little bit tricky. And once you've got the idea of finding moments, then the rest of it is easy. Once you realise you need to do clockwise moments or anti-clockwise moments, if you can find the moments, it's not too bad. If you have to stop and get stuck every time you're trying to find a moment, then it's going to be tricky. It's a bit like if every time you got to a point in the question where there was a quadratic equation to solve, you had to stop and think really hard about solving quadratics, then an awful lot of this book, an awful lot of this course would be really hard, wouldn't it? But if you get your quadratics so good that you don't have to stop and think about those, then you can sort of swiftly move through the rest of it. I think that's good advice. It's the same sort of idea when it comes to moments. So, what do we mean by a moment? Well, this is what we mean. If I have, let me try and start waving things. So, if I've got a pen here and I push down, then I'm making a turning force. Okay, I'm making the pen turn around the point where I'm holding it here. Now, if I push down with the same force closer to where my fingers are, the moment is different. The further away that I push, the sort of more of a turning force there is. Okay, now if you've not met that idea before, just think about it as on a seesaw. If you've got people, if you've got somebody on this end of the seesaw and someone on this end of the seesaw, and they weigh about the same, then the seesaw works nicely. Now, if this person here is a lot heavier, the seesaw is going to go down this side and it's going to go up this side, and it's going to stay there, isn't it? But what you could do to make the seesaw work is if this person here gets closer in, then actually the turning force from this person, the turning force from this person can be about the same, and the seesaw can start working again. Or if you think about levers, okay? If you have a lever, let's say you've got a weight here, the way a lever works is that you put a fulcrum, a pivot here, you've got a heavy weight on this end. If you try and push down on the lever here, you'll have a lot of hard work to do, but if you make the lever long enough, and you push down here, then it'll easily lift this up. And that's the way the lever works, is it's using this idea that if you're a long way away from the pivoting point, a smaller force will have the same turning effect. So that's hopefully what your life experience tells you. And how does that match up to the maths? Well, the math says if you've got a point here and you've got a force acting in a direction like this, then you need this distance. Now the distance is the perpendicular distance to the line of the force, okay? And the force times distance is your moment. So if we think about that, the moment, the turning force or the turning effect is the size of the force times the size of the distance. So if you push harder, if you have a bigger force, you get a bigger turning force, you get a bigger moment, okay? On the other hand, if you push with the same force but you push further away, then you get a bigger turning effect. Okay, you get a bigger moment. Moment is just turning effect, or you can say turning force, but force kind of means force, doesn't it? Right? A force is a push or a pull. So calling it a turning force is slightly odd because we're using the word force in a strange way. But you know what I mean when I say turning force. Turning effect is a bit more accurate, but a little bit of a weirder way of saying it. So suit yourself either way. But force times distance, that's the key idea. Make the force bigger, make the distance bigger, and you make the turning effect bigger. Obviously, if you make them both bigger, then you make the turning effect bigger as well. Now, that's all well and good when we have a nice example like this, and I say, okay, I've got somebody here who is pushing down with a force of 10 newtons on this little seesaw, and the distance that they're away is 3 meters. So it's an odd seesaw, but never mind. So the moment is 3 times 10. So it's 30. The unit's newtons times meters, aren't they? So 30 newton meters is my turning force. Now, that's fine, that's easy, but what if what happens is that I have a point here and I have I have a force which is not at 90 degrees to it. So if I'm pushing in this direction, and I'll take the example here from example 1 actually. So if I've got a force that's going this way in 12 newtons, and what I know is that it is 8 meters at an angle of 35 degrees from my point P, okay? Now the problem is that my force times distance, that distance has to be the distance perpendicular, right? There has to be a perpendicular distance to the line of the force. So the distance that I actually want is this distance here. Now the first way to deal with this is to do it in this way. I can think of that distance there as a distance in this triangle, 8, 35 distance. So 35 is, now let's do this carefully. Sine 35 equals d over 8, so d equals 8 sine 35, and of course we're in degrees here, okay? Now, if you're not yet used to this idea that if you've got the missing part of a triangle, you can write it down as 8 sine 35, so that's the hypotenuse, sine because this is opposite, so d equals 8 sine 35. You want to be able to go straight to this without having to go through this step every time, okay? Now if you're not used to it yet, don't worry about it, you can get used to it, but you'll find that it's going to save you an awful lot of time if we can go straight to here. So d is opposite the angle, so I'm going to use sine instead of cos, so 8 sine 35 is this distance here. So one way of doing it is 8 sine 35 is the distance to the line of the force. Now sometimes what you have to do is extend the line of the force. So you might have a diagram that looks like this. Let me try and draw a good one this time. So if this is 4 meters and I've got a force going in that direction, which is 3 newtons. Well, if I try and go perpendicular to this force, as the diagram's drawn at the moment, I can't do, because if I'm going to go from this point to this line, there's no way of doing that perpendicularly. But it needs to be perpendicular to the line of the force. So extend that line as long as you want. Okay, so there's my force, there's my extended line that's going in the direction of the force. That distance there is the one that I want. So if I say that this time is 30 degrees, then this is opposite the 30 degrees, so 4 sine 30 degrees is going to be my distance. So the moment created by this force on this point here is 3, which is the size of the force, force times distance, 4 sine 30 degrees. Okay? Couple of other things to say here. First of all, when you see these sorts of diagrams for the moment, picture it like this. Picture it as you've got a point here, and it is a point on a sort of flat glass, flat sort of piece of glass, which you can push around. Okay, so this is the point that's kind of fixed in the middle. So the whole thing, or a piece of paper if you like, so it's kind of sliding around like this. So when I apply a force in this direction on this flat thing that's lying on a smooth surface, if you like, so it's going to slip around any way you like, there's no friction involved, it's just the only thing that's moving it is the forces that I'm pulling it with. Then when I do that, the whole thing's going to rotate this way. So if I put that force in, then this thing's going to rotate that way, clockwise. If I put a force in over here, then this force is going to make it go clockwise, this force is pulling it back anti-clockwise. All right? So that's the way to interpret these kind of diagrams for the moment. And there's one other thing to do, which would be this. Let's say that I have a distance here of 5 meters and a force here of 10 newtons. Let's keep the numbers nice and easy. And let's say this angle here is this time 20 degrees. Now, what we've said is that the way to do this is find that distance. So force times distance gives us the moment. Now the other way of thinking about it is this force, we could think of it as two component forces in this direction and this direction. Okay. Now if a force is going straight through this point here, it's not going to make this piece of glass turn around this point here, is it? If I push that way, there's no turning force coming from that from that force, not around this point at least, okay? If I push on that pen, I'm just moving the pen. If I were to push sort of around here, then it makes the whole thing turn around, okay? So if I were to push on this piece of glass here, then it makes it turn. If I were to push straight on the pivot, then it's not going to make the thing turn. It might have some other sort of effect, but it's not going to make the thing turn. So this part of the force, this part of this 10 Newton force going through there doesn't have a turning effect. This part of the 10 Newton force, though, does have a turning effect. So how do we square that with what we just said? Well, we do it this way. Think of this 10 Newton force as this horizontal component and this vertical component. And this vertical component is going to be this size here, isn't it? So I'm just going to draw it over here, even though it's actually acting here. So how big is this vertical component? How big is this horizontal component? Well, if that's 20 degrees there, then this thing here is 70 degrees, and this thing here must be 20 degrees again. So this component of my force here is 10 newtons, which is the hypotenuse of this triangle. I'm not going to put the newtons in, so 10 times sine of 20 degrees. So 10 sine of 20 degrees, okay? And what's the distance away from this point? It's 5 meters. So 5 times 10 sine of 20 degrees, okay? The other way of finding this moment is to find this distance here, which is, well, here's my right angle triangle. 5 is opposite the 20 degrees, so 5 sine 20 degrees times by the force, which is 10 newtons. And can you see that that way and that way we get the same answer? So one thing to do is to extend the line of the force. Draw a perpendicular line from your point to the line of the force, and you do that distance times the whole of the force. The other way of thinking about it is split the force up into two components, one that goes straight towards the point and one at 90 degrees to that. The one that goes straight towards the point doesn't have a moment, a turning effect. The one that goes at 90 degrees does have a turning effect. The distance is then the distance that you've got, and the force is then this one that you can work out with trigonometry. Either way, the moment comes out as the same thing. Okay, so everything we know about forces, we can think of them as in different, as separate components, or these two component forces would make a resultant force of this. All of that will still work, and we can split forces up into components, so we can combine component forces, and whatever we do with those forces that way, when we then come to find the moments, it'll all work out perfectly well. The moments aren't going to change depending on how we've thought about the forces, which, if you think about it, of course they don't, right? If I draw the forces differently, it's not going to mean that the turning effects are different. So those are all the techniques we need for exercise 4A. Oh, sorry, there is one example that I missed out, which is sort of an obvious one. A silly one to miss out, I should say. When I say obvious, that's what I mean. If I've got this sort of thing, so this force is trying to turn this page this way, that is clockwise. This force is trying to turn this page this way, that's anti-clockwise. So the clockwise moments, I'd say like this, clockwise, I've got 5 times 2, because this is 90 degrees, so it's simple. This one, I've got anti-clockwise moments. Or what have we got? Well, I think the way I'm going to do this is, oh sorry, that force is 8 newtons there. I'm going to think of it as 2 sine 50. Feel free to work that out a bit more carefully if you like, but 2 sine 50 is this distance here, times by 8 newtons. What's the overall force? What's the overall moment, the overall turning effect? Well, it's this in the clockwise direction, this in the anti-clockwise direction. So the overall turning effect in the clockwise direction is that, take away that. Now, if that turns out to be negative, if the overall turning effect in the clockwise direction turns out to be negative, then this thing must be moving anti-clockwise. If the overall turning effect in the clockwise direction is positive, this thing turns out to be moving clockwise. And if we look in example 2, this whole thing turns out to be 12.3 meters anti-clockwise, 12.3 Newton meters anti-clockwise, 10 Newton meters clockwise. So anti-clockwise, take away clockwise, leaves a total turning effect of 12.3 Newton meters anti-clockwise. So this thing would actually be going anti-clockwise. As much as this force is pushing that way, trying to stop it, this force is winning, and the whole thing gets to move that way. Okay, so good luck with exercise 4A. Do it as carefully as you can. You're going to need those techniques. Good luck.